Let's look at now what we do when we have a definite integral of a composite function. So notice that there are limits of integration. That's why it's a definite integral. Let's go through the thought process that we have been doing for composite functions. I notice there's a group, this function raised to the third. So I identify what is my inner function. Off to the side, I say this guy is my u, 1 minus 2x. I differentiate with respect to that variable, so du dx is negative 2. I need to get rid of the dx because this is u, so everything has to be in terms of u. So I multiply by dx and divide by negative 2, and therefore dx is du over negative 2. So this comes out du over negative 2 in its place. Let's do some substitution now. So I rewrite my integral. This became u to the third du. I could say over negative 2, or I could bring this out. I like that better. It makes it a little bit simpler. Notice, though, I did not write my limits of integration. Why not? Here's why. This and this is saying go from x equals negative 1 to x equals 0. But I've changed so that everything is in terms of u. That means I have to change the limits also. If x equals 0, let's figure out what does u equal. Well, if u equals 1 minus 2x, let's use that. If x is 0, 1 minus 2 times 0 makes 1. So our new upper limit is 1. If our lower limit was negative 1, x equals negative 1, that means u equals 1 minus 2 times negative 1, or 3. Our new lower limit then is 3. So see how we change everything in terms of u. Then it's just the value that we end up with. So now let's do our antiderivative. Keep our constant multiple out here. Antiderivative of u cubed is u to the fourth over 4. Put our brackets, say from 3 to 1, and remember how we go. Now it looks backwards because it's usually low number to high number. Don't go by what it looks like, go by where it is. So the fundamental theorem tells us that we plug in the upper limit first. So I have negative a half, plug in the 1, 1 to the fourth over 4, minus, plug in the 3, 3 to the fourth over 4, and simplify. So we end up with negative a half times, that looks like 1 minus 81, so negative 80 over 4, and therefore 10. Our final answer is a number when it's a definite integral. Definite integral gives us a number. Now here's something that you might see done elsewhere. Notice that we never had to change back to x because our limits were in terms of u. Sometimes what you will see is instead of that, instead of going this route, which I think is the easiest, you might see this. Negative a half, we've done the antiderivative, times the u is 1 minus 2x to the fourth over 4. But if I'm plugging back x's, I need those to be x's, negative 1 to 0. Then we'll plug in the 0, we'll plug in the negative 1, and eventually we'll get to the 10, but it's a lot more stuff that we have to plug it into. Essentially, we're doing the same thing. We just plugged in that stuff earlier to simplify our integral. Go the way that I suggested. It is the easier way. Why don't you give this one a shot, come back, and see how you did. Welcome back. Did you make this stuff in the radical the u? Let's see what happened. U is 1 plus 2x squared. Did you do the derivative of that u with respect to x? Let's see what you got, 4x. Did you do the solving for dx? You should have du over 4x. Did you substitute it back into the integral, du over 4x? What happened? The x's canceled out and only the x's. We're left with 7/4. Let's pull out the 7/4 integral, 1 on top over square root of u and a du. Did you remember to switch the limits? X is 0, x is 2. Let's use this to switch our limits. So x is 2 on the top. That means u is 1 plus 2 times 2 squared. or 9. X is 0 on the bottom. That means u is 1 plus 2 times 0 squared, or 1. And therefore our new limits go 1 to 9. Don't forget to switch those limits. Now let's rewrite this antiderivative, this integral, because that's a radical and it's in the denominator. So bring it up as u to the negative 1/2 du, and now we can do the anti-differentiating. 7/4 on the outside, add 1 to the exponent, divide by 1/2, or better yet, multiply by 2. Put our brackets 1 to 9. Perhaps we simplify this a little bit first. So 2 goes into 4 2 times, so let's make this 7/2. Instead of u to the 1/2, think of it as square root of u. Now we'll plug in our limits. So 7/2, square root of 9 minus square root of 1. 3 minus 1 is 2. So it looks like 7 in the end. Remember, it's just a number when we have a definite integral. Why don't you try the last 4? They're AP problems. Come back and see how you do. This is one that I see, this type of problem that I see often on the AP exam, where they're looking to see if you understand the U substitution rule. So they're saying what U is, and U is just that inside right there. So you know that when you do the U substitution, it's going to be square root of U. Well, all of those have it. Notice what's different. Some of them don't have a constant multiple of 1/2 outside, and some of them have different limits. So let's go through our whole process of what we do when we identify the u. We find the du dx, we solve for dx, and we plug it in. Dx is du over 2, so what do I need? Something with a 1/2 on the outside, so it won't be this and it won't be this because they don't have a 1/2 on the outside. What else do I need to do? Change the limits of integration. If x is 0, then u is 2 times 0 plus 1, or 1. If x is 2, u is 2 times 2 plus 1, or 5. So my limits are no longer 0 to 2, but 1 to 5. There it is. Number 10 is just another way to ask the question. dy dx equals cosine of 2x. What's y? This is just saying go from derivative to not derivative. This is saying to integrate or take the antiderivative. So we're doing the antiderivative of cosine of 2x with respect to x. So do our steps. Identify the u. U is 2x. Take its derivative. Solve for dx. It's du over 2. You know that means we have a 1/2 to bring out. Cosine of u du is left. What's the antiderivative of cosine? It's sine. U is 2x. Don't forget about the constant multiple of 1/2, and don't forget about plus c. Remember always to plug back in what u is. Average value, give it a shot. Remember the formula for average value of the function. 1 over b minus a times the integral from a to b of f of x dx. The reason I stuck this in here, just to give you some practice with average value and u substitution rule. So we're setting up 1 over 2 minus 0, integral from 0 to 2 of x squared, square root of x cubed plus 1 with respect to x. What's our inside function? Do the derivative. Now let me show you something that is a way that you'll see some people do this. I see the u. I see the derivative of the u is 3x squared. Well, here's an x squared, so I know that this is my du dx, so this with this is part of it. I just don't have the 3. So I put the 3 here and I balance it with a 1/3. That's what some people do in their process, and it gets rid of the having to do plugging in some substitution. It tends to be a shorter way, but sometimes not necessarily the easier way. That's up to you as you practice and learn how to do these. So we have 1/2 times 1/3, or 1/6, the integral from Well, it's not going to be 0 to 2 anymore, so I'm not going to write those. Instead, it's going to be, let's see, all of this part was with our du dx. So square root of u times du in there. And then we can do our antiderivative. So 1/6 u to the 3/2 times 2/3. Not going to do plus c because I'm going to figure out what those limits are. So doing a substitution of our limits 0 to 2, 0 will give us 1, 2 cubed is 8 plus 1 is 9. So this will be from 1 to 9 instead. Simplifying this, putting in the 9, let's see, this is 1/9 on the outside, and u to the 3/2, or 9 to the 3/2, which means square root of 9 cubed minus square root of 1 cubed. Remember, the half is square root. Gives us 1/9. 3 cubed is 27 minus 1, so 26. So times 26, or 26 over 9. Average value. Another example, just to give you some variety, a particle moves along the y-axis so that the velocity is given by this. S of t being the position, given this initial condition, find s of 2. So if this is the velocity and the position is s of t, we want to know the position at 2. We want to find the position. So that's the antiderivative of t sine of t squared. And taking that antiderivative requires doing a u substitution because we have more than just t. So if u is t squared, this time we're doing du dt to t. Solving for dt, we have du over 2t. So plug in that spot, du over 2t. I see the t up here, gets rid of that one. Good news. Don't forget about the half. Pull it out. 1/2 integral of sine of u du, or taking the antiderivative, 1/2 negative cosine of u plus c, and then plug the u back in. So -1/2 cosine of t squared plus c. Well, the plus c we can find because they gave us this initial condition. This is the position, so when the position is 3 at time 0, we get c to be 7/2. Plug that back in to the position function, s of t equals -1/2 cosine of t squared plus 7/2, and now we can use that to find s of 2. So s of 2, -1/2 cosine of 2 squared plus 7/2. Compute that, and we can't get an exact answer unless we pull out our calculator, which we won't. Cosine of 4 plus 7/2. Yay.